Section 317 is called heat required to raise the temperature of a body. And what we're going to be able to do with this section is to quantify some variables that give us a precise calculation of amount of energy required, or the amount of time, the change in temperature, excuse me, and the mass of the object. And so let's look at the components of this. So here's our equation. It's equation 317 in section 317. And it says the heat is equal to the mass times the specific heat capacity of the material. Okay, so this is a characteristic of materials, and every material has a specific value for that. And we'll need a lookup chart or table to be able to find that. And then delta T is the temperature change. All right. And so this allows us to make some determinations, right? In terms of, how much energy would I have to supply to raise the temperature a certain amount? And we'll look at a direct application of that. And first, let me show you where we find some of these values, specifically where this table is for specific heat capacity, because we're going to be able to need to look those things up. So here's this very useful table. It's called table AX2. It's in the back of your book, page 910 in the 6th edition. And so what it has across the top here is certain materials, the chemical symbol or composition of the material, the electrical properties, the mechanical properties, and the thermal properties. And all of these things will come into consideration at some point during the course. And you can see that, we've got resistivity of in terms of electrical properties. And, you visited that in ELC 131, where you determined that, copper had a certain resistivity, silver had a certain resistivity, and, it varies based on the temperature and so forth. Then there's that temperature coefficient that gave us another consideration with that, so we could look at what the resistivity was or the total resistance at different temperatures. Thermal properties are listed here, mechanical properties here. Now, what we're concerned with right now is this specific heat capacity, and it's in some units that we're not probably real familiar with. Joules divided by kilogram degree C. All right, again, we're not looking to derive this stuff. We're just going to use it and take it that way. And then for this particular problem, we're dealing with pure water, he says. And, all water composition varies a little bit based on the minerals and all that might be dissolved in it. But for this particular problem that we're going to look at, we're going to need to know the specific heat capacity of water. And I'm just going to go ahead and write that down for us. It's going to be 4180 joules per kilogram degrees C. And of course, that's, all these are just lookups. You'd never want to try to commit yourself to memorizing anything like this. It's much more beneficial for us to have these lookup charts and appendixes and so forth to be able to do this with. So we get back to our problem. It says, calculate the heat required to raise the temperature of 200 liters of pure water from an input temperature of 10 degrees C to an output temperature of 70 degrees C. Okay, so this is a real problem. I mean, you could run into an application, involving something like this. How much energy, heat energy, would I have to input into this container of 200 liters of water to raise the temperature 60 degrees? And of course, I have a formula that allows me to do this, and that formula is 317. And let me do something right quick. I just want to show you one thing here, and just to make a point here before I go to the next stage of this. Okay, I'm going to apologize for that pause there. What I was trying to do in this problem, he tells us, we looked up what the specific heat capacity of water was in the appendix, and we found that to be 4180 joules per kilogram degree C. And he tells us in the problem that 1 kilogram of water 1 liter of water weighs 1 kilogram. Okay, and I was going to show you where to find that and all that, but I was not having luck finding that. So we're just going to go with what he's telling us for the time being, and then we'll see other examples of this down the road. Okay, so we've got all the information that we need to plug into our problem here. So the thing that I was getting there with, I've got 200 liters. Each liter weighs a kilogram. So as I go to plug into my equation, Q is equal to 200 kilograms for 200 liters. And the specific heat capacity is this 4180 joules per kilogram degree C. And then the change in temperature is the difference between 70 out and 10 in, which is 60. Multiply that out, and I get 50.2 megajoules of energy that's needed. Now, I want to show you something that's I think it's kind of cool, because we're going to relate this to something we think more of in terms of electricity. So when we went through the problem, what we found, or what our calculation, or equation 1317 gave us, was megajoules of energy, right? And so look, we can convert, if you look where the cursor is, we can convert, here's one of the conversion charts from the first part of chapter 1, and we can convert from megajoules to kilowatt hours by dividing, going against the arrow, dividing 50.2, which is what we found, 50.2 megajoules divided by 3.6 will give us kilowatt hours. So maybe you're saying, oh, okay, so what's the big deal about that? Well, what this tells us, and maybe you remember this from 131, but we measure electrical energy in terms of the amount of power use over time, right? And so generally when we talk about electricity, it's measured in kilowatt hours. And so this would be the electricity requirement to input this amount of thermal energy into this tank to raise this 200 liters from 10 degrees to 70 degrees. Okay, now again, now we're getting somewhere, right? We're getting into some real things, and ultimately I hope we bring all this together, and we think about the applications and how we can use this in a lot of different areas as we progress through with our electrical knowledge.